Hi, Dr. Oppenheimer.
Thanks for coming, Dr. Einstein. This is a semester emergency. We've got one hope. All of SCS's industrial might and scientific innovation connected here, a secret laboratory.
Don't worry, let's recruit some scientists.
Hi, Barbie. Hi, Barbie.
Hi, Barbie.
Hi, Barbie.
Hi, Barbie.
Hi, Barbie.
Firstly, we collaborate with other groups to acquire more than 200 images for each symbol. This includes all the different angles and distances. This ensures the diversity of our dataset. Then we upload all our images to RoboFlow so we can draw bounding box and annotate our images. To even further diversify our dataset, we apply augmentation techniques such as adjusting brightness, exposure, blur, adding noise, and incorporating rotation and shear. This approach helps prevent overfitting of our model and make it more adaptable to varying external conditions. After gathering and augmenting our dataset, we have an impressive collection of over 15,000 images. This extensive dataset allows our model to have an exceptional adaptability, but at the cost of increased computational demands. To address this challenge, we leverage Google Cloud Pro for training. After numerous iterations, experimenting with various augmentation techniques and model parameter combinations, we ultimately succeed in training our two-savior model, Week8.pt and train Week9sunlight.pt.
As the command center of our robotic system, RPi manages communication among the Android tablet, STM, PC, and RPi camera. We use Python's multi-threading to handle these interfaces concurrently. We have implemented message queues for each interface to ensure efficient communication. For example, if the PC thread receives a message from PC to STM, it will put the message into the STM message queue instead of directly sending the message. At the same time, STM thread keeps checking its own message queue to send messages. This approach keeps the interface always responsive while passing the messages.
The RPi also has some additional functionality unique to each of the tasks. For task 1, the pathfinding algorithm assumes that the turning radius of the robot is 30 cm. However, this is not the case. To address this, the RPi also sends additional forward and backward movement commands to the STM board to correct the robot's turning radius after each turn. In task 2, new commands were created for the STM board to return the distance between the two obstacles, as well as the length of the second obstacle. The RPi then used these distances to calculate the path to return to the car park before sending these commands to the STM.
So we retrieve obstacle data from the Android connected to the RPi. From there we can plan a Hamiltonian path.
But how do we calculate it?
Well, we can represent the obstacles as a graph. So the edges between the nodes will represent the Euclidean displacement between them.
Oh, but I think so we'll also need to account for the difference between the target and the position of the robot. How about we add a heuristic function for that?
Good idea. From there we can brute force a search for the best Hamiltonian path, given the small number of obstacles. Now, once we get a Hamiltonian path, how will we plan the route from point A to point B?
I guess we can use A-star search for that. And to approximate the cost of every node, we can add the distance from the total cost from the starting to current, and then we can also use the heuristic to find the distance from the current to the destination using Manhattan distance.
And then once we find the goal node, we can backtrack and then we can construct a movement string to send to the RPi.
The Android device focuses on delivering a user-friendly and minimalistic design. Bluetooth is used to ensure a robust connection with the RPi for seamless message exchange. Upon entering the Bluetooth page, scanning for new devices starts automatically, and users can simply select a device to connect to it. Next, our app has a special zoom feature to address the constraints of a relatively small screen size. Users can perform a pinch to zoom gesture to zoom in or out. This makes it easier and clearer for users to view the respective obstacles on the map. After clicking Start, a path will also appear to show the movement of the robot.
Being in charge of the STM, I am tasked to ensure that our robot operates as desired. Our robot is able to move straight, turn in an angle, and stop using either the ultrasonic sensor or the IR sensors. To ensure that the movements are accurate, PID controllers are used for error correction in the servo motor through the gyroscope and in the motor through the encoder.
I don't know if we can be trusted with such a weapon, but we have no choice.
Are you saying that there's a chance that when we push this button, we destroy the world?
Chances are near zero.
Near zero?
What do you want from theory alone?
Zero will be nice.
start.